Good morning, students. So in the earlier classes, we learnt about the ideal systems, which we have obtained the solutions of wave functions and the energy eigenvalues. And we solved the exact method of Schrodinger equation. And of course, we learnt a lot of models like quantum well models, infinite finite quantum wells, barrier problem, hydrogen atom, then harmonic oscillator, rigid rotator, and all those models in which we calculated the energy eigenvalues and wave functions of Schrodinger equation of Hamiltonian equations. So we know already. So this is ideal systems, exact solutions. Okay, and some of the system, most of the systems exist with non-idealist systems. So we'll have to go only with some approximation. So approximate solutions, we will get approximation energy, for which we thought about the perturbation method. So in perturbation method, the perturbation will take place especially in terms of potential energy. So there will be a potential in which some disturbance will take place. So at the time we corrected the energies and we added those energies with the previously known eigenvalue equation. So we added those energies with the corrected energies and we could calculate the energies. So this is what we learned, and in fact we learned two methods of perturbation, non-degenerate and degenerate. In non-degenerate method we could calculate the expectation value of the Hamiltonian perturbation, and in degenerate method we could be able to obtain the diagonalization of matrices of perturbing Hamiltonian, and we are able to get the energies, corrected energies. And another approximate method which we learned in the last class, which was on variational method, in which we guess the wave function. We guess the wave function. Of course, this is also approximation method for the bound states. We guess the wave function and we could obtain the wave function and corresponding energy eigenvalues, and we compare those values with the original values, true values, the energies which we obtained from the experimental values, and whichever is closer, that guessed trail wave function is the correct one. So this is what we learned. Then another approximation that we are going to learn is WKB approximation method today. Here also it's also an approximation method for the bound states as well for the tunneling rate. So we can calculate for bound states as well for the tunneling rate. So this is a model in which there exists Schrodinger wave equation, there exists a solution. The solution cannot be solved. So now the solution that we are going to obtain will be in terms of differential equation. So we have to have some approximation to solve the solution, to get the final answer. One point. Then another point is very important point is, it is a semi-classical method. Semi-classical method in which we are going to use the results of classical method and we are going to compare these two. So here in this situation, in WKB method, in which we are going to use both the results, quantum results as well classical results, and we are going to compare. And of course, in WKB method, the potential will vary slowly. In the sense, the variation of potential, as I said, it will be very low and it will be very slowly varying potential, and this will be exactly compared with the de Broglie wavelength, one de Broglie wavelength. Only then the WKB approximation will be valid. One. Then another one is, this is valid within the classical point of view, classical validation. We are going to see. Okay. Then another thing is, this will be useful only for the one dimension one, but also for three dimension one, this can be used for the spherical problems, spherically symmetric problems, especially when this condition is satisfied. When V of R vector equals V of R, so the spherical symmetric, at that condition we can use WKB method. Okay. So first point is, in WKB method, the potential will vary slowly, first point, in such a way that this variation of potential, it remains constant within one de Broglie wavelength. So that is very important point. Then second one is, it is a semi-classical method in which we are going to have some results from the quantum mechanics, and we are also going to compare these results with the classical results. So second one. And another third one will be, we are going to get the final answer that will be on quantization of phase space. Quantization of phase space which was obtained by Bohr-Sommerfeld model. So from Bohr-Sommerfeld model, that answer that will be compared with a quantization of phase space, in which the WKB quantization of a rule that we will have, exactly we will have it as allowed energies, so permitted energies. Okay. So with this introduction, then another very important thing is, the solution, as I said earlier, the solution cannot be solved. So we'll have to have some approximation. Okay. So in that approximation, we will be using amplitude and the exponential function, which will be the function of position, function of x. Okay. So with this introduction, we will start WKB approximation. So in the year 1926, Wenzel, Kramer, Brillouin. So Brillouin, almost all the three scientists, they independently discovered this one in the year 1926. But earlier, one mathematician named Jeffrey in 1923, he also discovered this method, approximation method. So that's why sometimes it is called as JWKB method. So Jeffrey, Wenzel, Kramer, Brillouin method. In some other book you may find as JWKB method. In some other book you will be finding this is a WKB method. Okay. So as I said, this is an approximation method. Okay. And this will work out for the bound state as well for the tunneling. So both the things this will work out. The solution that we are going to obtain as a solution, of course, but which cannot be solved. We'll have to make some approximation. Then we can solve. Okay. So this is the idea. Then very important thing is, the potential will vary slowly. Okay, almost it remains constant throughout one de Broglie wavelength. So this is the idea. So Wenzel, Kramer's, Brillouin approximation is a valuable technique for obtaining approximate solution of one-dimensional system. Okay, in which the potential V of x is slowly varying function of position. So dV by dx. Of course, we will be using only time independent Schrodinger equation. Okay, time independent Schrodinger equation. So potential depends only on x, not t. Okay. In a semi-classical method, it is based on the quantization of phase space. The final answer that we are going to get in this class, that will be based on quantization of phase space. The wave function is assumed to be an exponential function with amplitude. So we are going to have two solutions. One is phase factor, another one is amplitude, which are the functions of position, which are the functions of x. And this phase also slowly varies with the de Broglie lambda wavelength. It is used to obtain approximate solutions to the time independent Schrodinger equation, most of the time in one dimension, but also in some time it will be used in three-dimensional, provided V of r vector equals V of r. So this is the picture of Wenzel, Kramer and Brillouin. To find the energy eigenvalue in which the classical limit is valid. So we will get the solution in which, up to which the classical limit is valid. WKB approximation method is a semi-classical method and is based on quantization of phase space, which we learnt earlier just now. A slowly changing potential implies that the variation of V of x slightly over several wavelengths of de Broglie. So minimum will be one wavelength, and it can also vary with the several. So it means that V of x will remain constant for several wavelengths of de Broglie wavelength of the particle, moving with the energy in the region of potential. It implies that the potential is very slow and remains constant for one de Broglie wavelength, where only then the WKB approximation can be applied. And what are the applications? As I said, we can have two options. One will be the bound state, and another one will be the tunneling property. Okay, tunneling one. So mainly, so calculating the bound state energies whenever the particle cannot move to infinity, then transmission property, tunneling property through potential barrier. Scattering problem also it will be used. Then spin wave propagating through domains fall also, this will be used. So these are the applications of WKB method. Now we will go into in details about the theory of WKB method. Okay, we just consider this is one dimensional harmonic oscillator problem. We will consider. So now particle moves back and forth. Okay, we consider this is the particle that moves back and forth to and from motion, left and right. Okay, so in that case we can have starting the wave equation exactly like this. So we have a kinetic energy part, potential energy part, and total energy part. We know total energy is the sum of kinetic energy and potential energy. We know this one. So of course, it's very important thing is potential depends on x. We are going to consider more on this. So rearranging this term, that will have this equation. Okay, and this term can be considered as your k squared. So k squared equal to 2m by h bar square e minus a. Now we are going to have three cases. So earlier we are looking only two cases. One is E is greater than that of V. So this was a case which we studied already. Then second case will be E is less than V. Okay, E is less than V is total energy is less than that of potential. The potential is greater. So that is a very important case which we are going to discuss. Then another case will be E equals V. That is very important one. In WK method we are going to learn E equals V. Okay, the total energy is equal to V. What will happen? Okay, so now we will go for the first case. The first case says like this. Okay, so you have this equation. So this can be replaced by this one. So this equation. The solution of this equation is given by this expression. So we know already this is very simple. And of course plus or minus 1 is written because as I said the particle moves back and forth motion. So one wave goes from left to right, then another goes from right to left. Okay, so positive it means the wave traveling to right. So negative means wave traveling towards left. And your k will be 2 pi by lambda, and lambda is nothing but de Broglie wavelength. And k stands for quantum momentum. Okay, and of course k we know already, this is about the wave vector. Okay, this is another term that we call this as quantum momentum. Okay, now we will go for E less than V. So this case is very simple. E is greater than V, that we can follow. If E is greater than V, your total energy is greater than that of potential energy. So classical mechanics also will work out here. Okay, classical mechanics. So if E is greater than V, that means the kinetic energy is positive quantity. Okay, because you will have only positive quantity. The positive momentum will be there. Okay, so classically this will work out. Of course, quantum mechanics also will have the answer. But what about this case? In this case, E is less than V. If E is less than V, V is much more greater. So kinetic energy will be negative. So classically this is forbidden. Whereas quantum mechanically that happens that if E is less than V in this region, that tunneling will take place. So earlier model, this stands for the bound state, correct? This stands for the bound state, whereas this one stands for the tunneling property. So quantum mechanically this will work out, whereas classically this is forbidden region, where because the energy, kinetic energy is negative here. Quantum mechanically it's okay, whereas for classical mechanics it is forbidden because E is less than V. So kinetic energy will be negative. There is no negative kinetic energy in classical physics. So this equation again will have the solution of this equation. The potential is varying with the position. The potential, okay. Here also the potential is varying with position, but this variation is less than the particle's de Broglie wavelength. This variation is very low and slow, and the potential remains constant for several wavelength regions. So very important thing. So since the potential is very slow, we can assume that the measure of the wave function will not change, but the wavelength and amplitude will vary less. So in this case, the wavelength will depend on x and the amplitude also will depend on x. Okay, in slowly varying potential. So if the wave function is, so here also the wave function is sinusoidal. Here the wave function is sinusoidal, of course. And the outer part, that is the tunneling, after tunneling, that also will have a sinusoidal part, but it will vary slowly. Okay. So this sinusoidal remains the same. It remains the same even after tunneling. This is the main idea of WKB approximation. Now suppose the potential varies slowly. compared to that of wavelength. The WKB approximation treats the wave function in this potential as the same as oscillating function. Whatever may be the oscillating function inside bound, that will be the same oscillating function outside also, tunneling, but with a slowly varying modulation. But that will have the, after tunneling, this will have a slowly varying modulation in terms of amplitude and wavelength. So amplitude varies with x, wavelength also varies with x. So lambda of x, a of x. So there is one place in which the whole program is bound to fail in this case, if E equals Vx. So what will happen if E equals V? Now the total energy is exactly equivalent to potential energy. Suppose in this case when E equals V, when V equals V, potential energy is equivalent to total energy. So kinetic energy will be 0. Correct? So if there is kinetic energy will be 0, so momentum will be 0. Okay, in the sense, momentum, there is no momentum at all. So if it is so, in quantum mechanics, k squared equals, we know already 2m by h bar squared E minus V. So this term is equivalent, so this term must be equal to 0. Correct? If lambda equals 0, what would your, if k equals is 0, what would your lambda? Lambda becomes infinite. So exactly at this point, see at this point, E is exactly equivalent to V. Okay, at both the points, one is on the right side, another one is on the left side, traveling towards left side, traveling towards right side. So at both the points E equals V. Okay, if E equals V, lambda becomes infinite. Okay, what we call this as a turning points. Okay, in which we consider a particle, if we consider an oscillating particle, and this oscillating particle exactly will touch the turning point, one of the turning points, where the momentum is 0 at E equals V. Then it will start traveling in the opposite direction. So this will travel in the opposite direction. So at this turning point again, the momentum will be 0. Correct? The velocity will be 0. Again this will come towards in the opposite direction. So that's why we have oscillation. Okay, this oscillation will take place. Okay. So it implies that lambda becomes infinite. Just now we said we cannot say the potential is varying slowly here. These points are called classical turning points, in which the particle reverses its direction of its motion. This region is called classical region. So this region is called classical region. So if we consider the diagram exactly, so we are going to draw the graph between the position and the potential. Potential varies with position. Okay. Then we have the oscillating behavior. So oscillating behavior, and this region, first region, second region and third region, this region in which we have classical region. Okay, in the region, because E is less than V here. So now in this case, at this point, these 2 points are there exactly at E equals V, where kinetic energy equals 0. What we call is as turning points, in which the classical particle will reverse its direction. Okay, in this. So now what of this region, in this region and this region? So this is our non-classical region, because E is less than V. Here E is less than V. Here E is less than V. Both the points E is less than V. So in which there will be classical region. Okay, this is E less than V. So what we call this as E is less than V, non-classical region. Okay, so this will be our classical region. Here you have non-classical region. Okay, so this region is called a classical region, central region. So Schrodinger equation is given by, so we will have a general Schrodinger equation given by this. Rearranging this term, we will have this one, and of course we can take this term as P square. So what we call this as P as a classical momentum. Okay, so in the non-classical region, very important thing is the amplitude and the phase factor both depend on position, both depend on x. Okay, so this is about 3 cases. Now you can write d squared psi by dx squared, which can be replaced by, you have p squared, so p squared by h bar squared psi. The solution of this equation can be written as exactly like this. So a depends on x and the phase factor depends on x. So here we have phase factor. Okay, so now our aim is to find out a and phi and substitute here. Okay, and get the wave function. So this is our idea. So where a of x is the amplitude and phi of x is the phase of the wave function, the wave function must become variable in both amplitude and wave number. Okay. So momentum. Considering the wave moving towards the right side, just we will take only plus quantity e power I pi x. Here plus or minus. So we have taken, we will consider the particle that moves towards the right side. Okay, for the time being. Just to differentiate this. So now a depends on x. Your phi also depends on x. Okay. Now you are going to differentiate with respect to x. So just now we discussed about the potential which varies with the position. Okay. So a also will vary with the position, and similarly phi also will vary the position. So both depend on position. So now you are going to differentiate with respect to x. So keeping this as constant, you will have to differentiate this. Keeping this as constant, you will have to differentiate this. So that's the idea. So when you are going to differentiate this, I can write this as a prime. Keeping this as constant, e power I phi of x, plus keep this as constant, just differentiate this. So this is depends on x. So we'll have to d phi by dx. So instead of d phi by dx, I can write this as phi prime. So I a phi prime e power of I pi x. Is it okay? I pi of x x. Is it okay? Now differentiate this again. When I am going to differentiate this again, you have to keep this as constant, you have to differentiate, plus keep this as constant, you have to differentiate. Now we have three factors here. A phi prime e power I phi of x x. So we have three primes. So again we will have to differentiate this, keeping these two constant. We will have to differentiate this, keeping these two are constant. We will have to differentiate this, keeping these two are constant. So we will have to have three terms. Is it okay? Very simple one. So now differentiating this. Okay. So you have a prime means dA by dx. A dash is dA by dx. So differentiate. You will have a double prime. Keep this as constant. So e power I pi x. Plus you will have to differentiate this, keeping a prime as constant. So a prime, your differentiate this will give you I phi prime e power I phi of x x. Okay. Plus I differentiate this, keeping these two are constant, plus IA differentiate this, that will give you phi double prime, keeping this as constant, plus IA phi prime, you will have to differentiate this, that will give you I phi prime e power I pi x. Okay. Now just I multiplied by I, this will give you I squared, so minus 1, so that will give you with a minus I. Okay. First point. Second point is these two terms are similar. Just add these two, so you will get 2 times. Very simple one. So you will have d squared psi by dx squared term can be written as exactly like this. You compare this equation with 4.155. There we have obtained d squared psi by dx squared equals minus p squared by h bar squared psi. You just compare. And of course psi we know, psi equals a e power I pi x. So substitute here. So minus p squared by h bar squared, and instead of psi you substitute a e power I pi x. Okay, I pi x. And of course, okay, it's correct. So now compare these two. Comparing these two, this one, so we will have this term which is equivalent to minus p squared by h bar squared a. Okay. Now we just take now real part with real part, imaginary part with imaginary part. We will have some 2 solutions. Now just to compare this one. First we will take real part first. So this is your real part and this must be your real part. So real part which is equal to minus p squared by h bar squared a. Is it okay? Now these two terms we can pull a out. So a double prime equals a within bracket, you have these two terms. Right? Very simple one. Okay, you just take this term to right hand side and pull a out, you will get equation 4.163. This equation cannot be solved. You look at this equation, and of course we have obtained some solution, as I said. So this cannot be solved directly. So earlier, of course we could use for some other integrals we will be using Gaussian integral, a gamma integral. So those equations cannot be solved, can be solved easily. But this equation cannot be solved easily. So we will have to have some approximation. Okay. So what is that approximation? We will find out. this approximation is A prime and A double prime will be very, very, very low value. We said already that A of x is slowly varying quantity. It's very, very low value. So this is very, very low with this one and this one. Then we can neglect this one, almost it's equivalent to 0. So we can write this term is equal to 0. Is it okay? This term A double prime by A, which is equal to very, very, very slow, very, very low value. So this term is equivalent to 0. So this term is equivalent to 0. So we have phi prime whole squared equals p squared by h bar squared. Okay. Okay. So taking the square root on both sides, that will give you phi prime equals p by h. You just differentiate. So this can be written as phi. Of course, phi prime is nothing but d phi by dx. So d phi by dx equals plus or minus p by h. So d phi by dx. Integrating on both sides, that will give you phi of x. So we have found out phi of x. As I said earlier, in the wave function, which consists of your phi and a. Okay, we'll have to find out phi and a. So we have found out now phi. What is the integration of px dx? Which is nothing but quantization rule, which was introduced by Bohr-Sommerfeld. Okay, so classical mechanics. Okay, so your phi of x equals plus or minus 1 divided by h bar integration of px dx. So one part is over. We have found out the phase factor in wave function. In wave function, there are two factors which we are going to find out. One is the phase factor, another one is amplitude. So phase factor we have found out. Now you just take the imaginary part. You compare the imaginary part on both sides. So this will be your imaginary part on the left hand side. There is no imaginary part on the right hand side. So that will be equal to 0. Multiply on both sides by a. Multiply on both sides by a. So we have taken this equation. So this is your imaginary part. Okay, we have already taken real part and we got the results for phi. Now we are going to take the imaginary part. Okay, so multiply on both sides by a, that will give you this equation. Now this equation can be written as d of a squared phi prime. Okay, this equation, how it is possible? Just you have to differentiate with respect to x, a squared phi prime. You will get these two terms. Come on, 2a, see 2a, a prime, phi prime. Another one is a squared, phi double prime. So these two terms can be simplified as differentiation of a squared phi prime, which is equal to 0. Okay, so this implies that a squared phi prime equals, you have to integrate on both sides. This is integration constant b squared. So you will get a squared phi prime equals b squared, a equals b divided by phi prime. Okay. Now your phi prime equals p by h. Just now we learned phase factor, which is nothing but p by h. Okay. So substitute here. So substituting, that will give you root p divided by root h bar. So root h bar b. This is a constant. H bar is constant. B is also constant. So put together, this is another constant. So c divided by root p, which is nothing but your a. So we have found out a of x. We have already found out phi of x. Okay. So complete your wave function will be a and phi of x. Okay. So we have found out a of x and we have found out phi of x. The complete wave function approximate for the approximate method, using WKB method, this is nothing but psi of x equals c divided by root p e power plus or minus I by h cross integration p of x dx. So this is your complete wave function using WKB method. And of course your psi of x alone will not give you any meaning. So you have to multiply always with its complex conjugate for probability density function. So you have to multiply its own complex conjugate. So that will give you multiply its own complex conjugate, that will give you probability density function, which is nothing but c squared by p, where c plus and c minus in the expression are some constants. Okay, what does it mean? Your probability density function is inversely proportional to the momentum. So this momentum is a classical momentum. This expression is from quantum mechanics, so it connects both the things. So that's why it is termed as semi-classical method. So this is classical momentum. Okay, classical momentum of the particle for the harmonic oscillator, which you have taken the example. So probability density is inversely proportional to the classical momentum in the classical region. Okay, it's very important one. So one side we have quantum, another side we have classical momentum. So we have probability density is the quantum concept, then the momentum will be the classical concept. Okay, now both are inversely proportional. It implies that if P is more and this will be very less. Okay, if it is more and this will be very less, when this will be more and when this will be very less in harmonic motion. Suppose if we take harmonic motion, okay, the harmonic motion which goes back and forth motion. Okay, so we'll have a potential, and suppose if it goes here exactly, it stops somewhere where the velocity is 0. Okay, almost 0, correct. The momentum will be very, very low, the velocity will be very, very low, where we can find the particle more. The probability of finding the particle more where P is very less. Suppose if we consider the motion of the particle the mean position, the velocity will be very, very, very high, the momentum will be very high. What of the position? We can't find out the position will be very low, correct. So the probability of finding the particle if this mean position will be very low, where the momentum is very high. So exactly we can, this is the result of WKB method. Okay, so the probability of finding the particle is smaller in those regions where it is moving rapidly. Okay, particle will spend least time at the position where the velocity is maximum. This is at both the ends. Because of high momentum of the particle will move fast down, it has to come down. So conversely, the particle will spend lot of time at the position where the momentum is low. So this is the idea about WKB method. This is the main result. Okay, equation 4.173. What is the validity of WKB approximation? Where it is valid? It's a very important thing. So as we said that the potential depends on position. One. Second one is slowly varying potential. So slowly varying potential in the sense dV is very, very less than that of dx. If it is so, then mod of dV by dx will be less than that of 1. So this is, of course, we know the condition. So this is the condition. And of course we know that k squared equal to this one, and k is directly proportional to v to the power 1 by 2. Okay, of course we know both are directly proportional. Okay, so instead of dv by dx we can write dk by dx, which is very less than 1. Okay, according to this condition. So k is also function of x, v is also function of x. So very important thing. Okay, so we know that lambda equals h by p from de Broglie's concept. So p can be written as h bar k. So this h bar k can be written as h divided by 2 pi. So 2 pi h divided by h k, and both will cancel. You have 2 pi by k. So k equal to 2 pi by lambda. You differentiate with respect to x. Differentiate with respect to x. So we'll have dk by dx, which is equal to, we'll have to differentiate lambda with respect to x. Okay, this is 1 by lambda. So minus 1 by lambda squared d lambda by dx. And of course your 2 pi is here. Is it okay? Just take mod 2 pi by lambda squared d lambda by dx. Just now we said dx by dx is very, very less than that of 1. Just now we saw, we can say it's very, very less than that of 1. Is it okay? So if it is so, just pull constant out. That also will be very, very less than that of 1. You just take 1 lambda out that side, or multiply by lambda on both sides. You will get this. Okay, this is the validity of WKB approximations. If this condition is satisfied, then this problem of WKB method will work out. So this is the validity. Then another idea is in terms of momentum also we can say. So we know that lambda equal h by p, differentiate with respect to x, lambda. So d lambda by dx equals again 1 by p. We will differentiate with respect to x. That will give you you have 1 by p square dp by dx. Of course h is constant. If it is so, you can write this as exactly like this: h divided by p square dp by dx d lambda by dx. D lambda by dx. Okay, d lambda by dx can be written as your lambda squared. So this can be written as lambda, less than lambda squared. Is it okay? Come on, I repeat, this d lambda by dx is nothing but less than that of lambda squared. Okay, lambda squared. So that's why we can write this term as very, very less than that of lambda squared. Okay, is it okay? So as usual, I can multiply and divide by lambda here. Okay, I can pull this lambda, that will give you 1 by lambda h divided by p square dpi by dx less than that of lambda. I can pull one lambda here, we will get this. Simple. Just take one lambda here. See, one lambda here. And what is lambda? Lambda equals h by p. H will get cancelled. This pp will get cancelled. So you can write 1 by p dp by dx less than that of lambda. This is another condition, another validity condition for WKB approximation. So this applicability of WKB approximation, this one and this condition, is that a fractional change of momentum over a de Broglie wavelength of particle is very, very small. So this is the validity of WKB approximation. So for the conclusion, WKB approximation serves the purpose very well in the region where the potential varies slowly. Okay, very important thing. So almost it remains constant throughout one de Broglie wavelength or several de Broglie wavelengths. However, at turning points, okay, at the turning points, classical turning points, wavelength becomes infinite where E equals V, infinite, and WKB approximation is not valid. Okay, so in this condition, because lambda becomes infinite, k becomes 0, lambda equal to 2 pi by k, so k equals 0, lambda becomes infinite. So this is not valid at this point. Okay, at the turning points. Now we will go for the connection formula. Connection formula means where it connects the quantum mechanics with the classical physics. That's called a connection point. Okay, so of course we learned both the things in the particular region. Okay, we learned, and this is not valid exactly at the turning points we learned. Okay, classical turning points also we learned. So turning points of classical motion are the points where the velocity of the particle vanishes and changes its sign. It vanishes or changes its sign exactly at these points. Okay, it reverses its direction. They are defined by the equation E equals V of x. So at the point, both the points E equals V of x, this condition is satisfied. Okay, E equals V of x, in which the particle reverses its direction. Momentum becomes 0. Lambda becomes infinite. So at turning points, wavelength becomes infinite. As a result, WKB approximation is not valid in the vicinity of turning points. To obtain the complete solution, Schrodinger equation is solved in the region of suitable extension surrounding the turning points, and then this solution is suitable joined to the solutions on the two sides. We are going to see. So these solutions are the wave functions in region where WKB approximation is valid. It is necessary to point out that WKB method can be used in the problems in which we have two regions where the WKB approximation is valid but which are separated by a classic turning points. For example, just take this graph. So in this graph, this point, so in this region, so maybe region 1, so E is greater than that of Vx. In this region, E is less than that of Vx. At this point, E is exactly equivalent to the Vx. So this point is the connection point where it connects quantum region with the classical region at this point. Okay, so from the figure it which the particle of energy E encounters a potential function V of x, region 1, where E is greater than V of x. So classical region. Region 2 will be E is less than V of x. It's a non-classical region, only quantum region. But both are separated as the turning point. This is the turning point at the point A. Classical turning point A. That point corresponds to E equals V of x. The equations connecting the WKB wave equations, wave functions in the classical and non-classical regions are given as the name connection formula. Okay, so this is called the connection formula, especially at this point where it connects both quantum region and classical region. Okay, at E equals V of x. Then the last slide. Last one is nothing but WKB quantization. As I said earlier, that we are going to have the solution that will be equivalent to exactly we have got the solution from classical region and we are going to compare these two. And of course we have compared. And the solution goes with like this probability of density function, which is directly proportional to c square divided by p. So inversely proportional to the momentum, one. And second one is this p of x dx. 1 by h bar p of x ds is nothing but quantization rule which we have obtained by Bohr and Sommerfeld earlier for the classical mechanics. Okay, classical region. And we are going to connect these two. Just take harmonic oscillator, and we have already explained this diagram earlier, and these two are turning points we know. So we have classical region this side, non-classical region on either sides. Okay, so we know already this. So the kinetic energy plus potential energy for this harmonic oscillator is given by this expression, we know already. And we have obtained already this expression also. Okay, we have obtained this expression earlier. Okay, using WKB method. And of course, we have also obtained this one earlier, n plus half h bar omega, we have already learnt from harmonic oscillator. So connect these two. This will give you the permitted allowed energies. This will give you n plus half h bar omega, or here h bar pi will give you allowed energies. When n equals 0, you will have h bar omega. When n equals 1, we will have 3 by 2 h bar omega, then 5 by 2 h bar. They are all allowed energies. So it means that this is oscillatory function. And quantum mechanics is speaking, so oscillation function will take place. Even in this region also, some oscillating function through tunneling behavior will take place. Okay, so this is the condition, quantization condition that determines the allowed energies. This equation provides the proper prescription for specifying the energy level for the harmonic potential well. So this is your harmonic potential well. For the larger value of n, the above quantization rule becomes semi-classical method. Okay, so that is the n. Thank you, students. We will see you in the next class. Bye.